Hello, my name is Julian. I'm an application scientist here at Micromeritics, and today I'm going to be talking about Physisorption data review and reporting. In this presentation, we're going to be covering three main topics: surface areas, pore volumes, and pore size distributions. These three techniques are commonly used for characterizing porous materials. For surface areas, the BET method is the most commonly used method to determine the surface area of materials. The T-plot method can also be used to determine the surface area by splitting out the difference between the micropores and the mesopore contributions of your material. Pore volume and size distribution methods include BJH and NLDFT methods. The BJH method is commonly used for mesoporous materials. Horvath Kawazoe method is commonly used for microporous materials, and DFT is an all-encompassing technique for determining both the microporosity and mesoporosity. However, the technique is very dependent on the chosen model, which are all based on different materials. First, we're going to look at typical Physisorption reports within the software. There are a variety of different report options for determining surface area, pore volume, and pore size distribution, which is shown on the screen now. First, we'll look at the isothermal report. The information shown here describes what type of data that you'd like presented. There's a variety of tabular reports as well as reports for plotting linear or logarithmic plots using the P/P0 axes, as well as absolute plots where you prefer to look at the absolute pressure units. Let's see how these plots look in our software. The tabular report will show a table of data including columns such as relative pressure, absolute pressure, quantity absorbed, elapsed time, and saturation pressure. Oftentimes, when looking at this report, you'll be interested in the relative or absolute pressure versus the quantity absorbed. Another area where this report can be useful is looking at the elapsed time. So you can see here exactly how long it took for each singular data point to collect and when it was collected during the experiment. This can allow you to look at specific areas where it may have taken longer than what you'd expected and potentially make adjustments to the method to speed up the analysis time if you're very time constrained in collecting your data. In general, as the relative pressure drops to below 0.01, it'll generally take longer for equilibration to occur in the smaller pores. Since you fill the small pores at the smallest relative pressures, oftentimes it takes the longest amount of time just due to diffusion of your adsorbing gas, such as nitrogen, into the pores of those materials. Additionally, the tabular report can be useful for looking at how the saturation pressure changes versus time. Normally, this should be very stable. However, if you're in an area that's very prone to large storms, you may find that if one of those rolls in, that the saturation pressure may drop considerably during your experiment. The linear plot shows quantity adsorbed versus relative pressure as P/P0. The logarithmic plot shows the same data, quantity adsorbed versus relative pressure, but on a logarithmic scale for the x-axis. This can be especially beneficial when you're most interested in those very low pressure points, and being able to distinguish them is much easier on the logarithmic plot compared to the linear plot. The linear absolute plot is exactly the same as the linear plot on the relative pressure scale, the only difference being that instead of P/P0, it's showing the absolute pressure in your chosen pressure units, whether that's millimeters of mercury or kilopascals. The logarithmic absolute plot shows the same data as the logarithmic plot, once again changing the x-axis to absolute pressure using your preferred pressure units. Typically, you'll prefer one of these four plots for looking at your isothermal data, and it will depend on your specific needs and where you're most interested in analyzing your adsorption points. The pressure composition plot changes things up a little and shows the absolute pressure on the y-axis and the weight % nitrogen on the x-axis. This is a different way of looking at these same isothermal data and can give you a sense of how much your material is adsorbing and what the total loading is of nitrogen on your sample. Additionally, with these reports, you'll have the ability to select how you want to see your quantity adsorbed on a per gram basis, which is most often used. However, you'll have the option to also do it per surface area or per another surface area. Next, let's move on to the BET report. In the BET report, you'll have several options for reports, including a tabular report, BET transform plot, and a BET isotherm plot. At the top of the options, you'll also be able to select a default setting for your BET range. In general, I'd recommend leaving this as the default between 0.05 to 0.3 P over P naught, because this is a standard fit range for mesoporous materials. At the bottom, there's a tab for pressures, and this will allow you to exclude individual points from your best fit range after you've collected the data. The tabular BET report shows relative pressure, quantity absorbed, and then the y-axis of the BET plot also shows BET surface area, slope, y-intercept, C-value, monolayer coverage, correlation coefficient, and the molecular cross-sectional area of your adsorbing molecule. In general, on a BET plot, the first things that I look at is the C-value and ensure that it is a positive value, as well as the correlation coefficient, and ensure that it at least starts with 0.999. If those two criteria are satisfied, then in general I know that I have a fairly good BET surface area data. Additionally, from those values that are shown in this report, you could calculate the BET surface area from the y-intercept and slope that is calculated for you. Next is the BET transform plot. Shown here is for a mesoporous material in which we selected points in the standard fit range from 0.05 to 0.3 P over P naught. You can see here the points that have been selected as they are noted by circles, whereas the points that are not selected are noted by triangles. In this plot, you should see a straight line through all of your adsorption points, showing that you have a good fit for your BET surface area. The BET isotherm plot shows your actual experimental isotherm data as well as your BET solution isotherm. And you can see that there's fairly good fit in the standard BET fit range between 0.05 to 0.3 P over P naught. Afterwards, however, there starts to be a discrepancy between the data, which is completely normal. The next reporting feature we'll look at is the T-plot. In the T-plot, there are two main reports, a tabular report and a T-plot report. In addition, you also need to select a thickness curve, as well as the surface area method. Most often for the surface area method, BET is chosen. For the thickness curve, there are several different options, and which option you choose will depend on your material. The Harkins-Jura thickness curve describes the value of the thickness without accounting for adsorbate-adsorbent interactions. This isotherm is mainly intended to calculate the micropore volumes, and it works well also when there are small mesopores. The Halsey thickness curve is related to a standard isotherm in the multi-layer region, thus is mostly used for mesoporous materials. Brokoff-de Boer proposed an empirical universal equation describing the thickness of multimolecular nitrogen adsorption on oxides and hydroxide adsorbents best applied to mesoporous materials with cylindrical pores. The T-plot tabular report shows a micropore volume, a micropore area, and external surface area, as well as slope, correlation coefficient, surface area, correction factor, density conversion factor, total surface area, thickness range, and the thickness equation. Oftentimes here you'll be most interested in the contributions of micropores and your mesopores to the total surface area of your material. You can see that the micropore area and the external surface area add up to the total surface area. In this case, it was determined using BET. You'll also be able to see the thickness curve as well as tabular data for relative pressure, statistical thickness, quantity adsorbed, as well as which points you're fitting. To know which points to fit, you'll use the T-plot. In the T-plot, you'll see quantity adsorbed on the y-axis and thickness on the x-axis. In general, you want to select your points such that there's a straight line through the micropore region of the isotherm. Typically, this will be somewhere in the range between 3.5 to 5 angstroms. The next report we'll talk about is the BJH adsorption/desorption. This report is most often used to determine the pore size distribution of mesoporous materials. It works very well for pores between about 30 angstroms up to a maximum of 1,000 angstroms. Once again, you will select the thickness curve. This thickness curve is the exact same one that we talked about for the T-plot method, and the same rules apply for selecting the appropriate thickness curve. You'll also select a BJH correction factor, choosing between Foss and Crook. The BJH tabular report has columns showing pore range, average pore width, incremental pore volume, cumulative pore volume, incremental pore area, and cumulative pore area. It can be a little bit hard to look at this data, and oftentimes you'll prefer to look at it in graphical form. The cumulative pore volume report shows the total pore volume on the y-axis and the pore width on the x-axis. When you look at this curve, I find it easiest to look at the curve from right to left instead of the standard left to right. Essentially what this curve tells you is that if we look at 500 angstroms here for our pore width, we essentially see that we have no pores in that range that contribute to the total pore volume of the material. We don't see a significant contribution to the total pore volume until we get to pores that are around 200 angstroms in size. We then see that there's a very large contribution to the total pore volume for pores between about 150 and 50 angstroms. We see that there's very few pores below 50 angstroms, as there's very little contribution there to the total pore volume of our sample. The differential pore volume plot shows the same data that we're looking at on the last slide, but instead of graphing cumulative, it's graphing the differential. What this means is that when we reach a peak, that corresponds to the largest quantity of pores in that particular pore size range. The data here matches up with exactly what we saw before, and that the vast majority of our pores are between about 50 and 150 angstroms. The same data can also be looked at on a logarithmic scale for the pore volume. The general shape of this curve will be very similar to the one that we saw in our previous slides. In general, you may find it easier to look at one report over another, depending on how large of a variety there is in your pore sizes across between 30 and 1,000 angstroms. Next, we'll look at the cumulative pore area report. Whereas before we were looking at pore volume reports, this report looks at the pore area overall. We see a very similar trend in the data as what we saw in our pore volume report, and generally you'll prefer to look at one or the other. Looking at the differential pore area report, we see a similar trend to what we saw here for our pore volume report, where the majority of our pores are between 50 and 150 angstroms. The next report is the Horvath Kawazoe report, commonly referred to as HK. HK is very complementary to BJH because it looks specifically at microporous materials, whereas BJH will consider the larger pores for mesoporous. The first thing you need to select in the HK report is a pore geometry. There are 3 options available for slit, cylinder, and sphere. Spherical pore geometry is just as you would imagine it, a spherical ball. A cylindrical pore can be envisioned as a circle extending indefinitely in the depth direction, and then a slit-shaped pore are those in which you have a top slab and a bottom slab, but there's no sides to the pore, and it extends indefinitely in the depth direction as well. So oftentimes, cylindrical and spherical pores are very common for crystalline materials such as zeolites, metal organic frameworks, etc., whereas slit-shaped pores are very common for amorphous materials and are oftenly carbons. Additionally, in the HK report, you can also apply the Cheng-Yang correction as well as smooth the differentials of the data. The first report is the HK tabular report. In this report, you'll see columns showing absolute pressure, relative pressure, quantity absorbed, pore width, cumulative pore volume, and differential pore volume. Much like the BJH reports, oftentimes you'll probably prefer to look at this in graphical form. On this report, you'll also see a median pore width as well as a maximum pore volume, and the specific relative pressure where the maximum pore volume was determined. The cumulative pore volume report shows the contribution of pores of that size or smaller that contribute to the overall pore volume. In this material, we can see that there is a sharp uptick around 5 angstroms and then a smaller one around 7.5. And then above 10 angstroms, there's a very small contribution of those pore sizes to the total pore volume in our material. We can also view the data as differential pore volume, where once again, the highest peaks will correspond to the greatest number of pores in that particular size range. This matches what we were looking at before, seeing pores that are roughly 5 angstroms and then another peak at around 7.5 angstroms. The last set of reports we'll look at are our DFT pore size reports. In these reports, you will need to select a geometry of which there are 2 options, slit and cylinder. And you will select that geometry for the same reasons that you would select in Horvath Kawazoe. Additionally, you'll also select a model. The model should be specific to your material and you'll only be able to see models that match the gas that you used for your experiment, as well as the temperature where you collected your data. We have models that are available for nitrogen at 77 Kelvin, argon at 77 Kelvin, and at 87 Kelvin, and then CO2 at 0 degrees Celsius. We also have additional videos if you'd like to learn more about DFT and selecting the appropriate model. The pore table report has columns for pore width, cumulative pore volume, incremental pore volume, cumulative pore area, and incremental pore area. Once again, oftentimes it's easiest to visualize this data in graphical form. The isotherm table will display the relative pressure, experimental quantity adsorbed, fitted quantity adsorbed, absolute residual, and relative residual quantities. Essentially, this shows you how well the experimental quantity matches with the fitted data. Once again, it may be easiest to view this in graphical form. The cumulative area report shows the pore width on the x-axis versus the cumulative surface area on the y-axis. Where you see the sharp uptick in the cumulative surface area corresponds to where there's a lot of pores in that particular size range. We can see here that the majority of our pores are somewhere in the area of 5 angstroms. We can also see that we essentially have no pores larger than 10 angstroms in size. The incremental surface area versus pore width report shows the differential of the last slide. Once again, confirming that our data shows that the majority of pores are roughly 5 angstroms in size. The differential surface area versus pore width graph should look very similar to the incremental surface area graph that we saw on the previous slide. It's showing the same data in a different way, once again showing that the majority of our pores are at the pore size of 5 angstroms. The differential area log width surface area versus pore width graph shows exactly the same data as on the previous slide, just with the different scaling of the x-axis. The cumulative volume graph shows the cumulative volume of all pores with respect to the pore width. Once again, we can see that there's a sharp uptick in the cumulative pore volume at roughly 5 angstroms, which corresponds to the majority of our pores in that size range. When we reach the maximum pore width in our DFT model here, the pore volume should be similar to the pore volume that we see when all of our pores are filled using the standard isotherm data. The incremental pore volume versus pore width graph shows the distribution of our pores. Whereas previously it was per surface area, now we're looking at it per pore volume basis. Overall, the general shape of the graph should be the same, and we would see that we have the same pore size distribution centered around 5 angstroms, which is where the majority of our pores lie. The differential volume versus differential width pore volume graph is very similar to what we saw for the pore area graph of differential area versus differential width. And we see similar results comparing the two. The main difference is the change of our y-axis variable, but overall the trend remains the same. Next up is differential volume over differential log width, pore volume versus pore width. Once again, this follows the same convention of what we saw earlier with the pore area. However, this time we're looking at pore volume. In general, this trend should remain the same, with the main difference being that we're looking at it in logarithmic x-axis compared to the previous plot. Next up is the log goodness of fit graph. This graph displays our isothermal data and our data points, which are shown in red, whereas the theoretical predicted isotherm, which is displayed in black. The overall data is plotted on a log plot on the x-axis. This makes it a lot easier to see the agreement between the experimental data and the DFT approximation of our data, particularly in the low pressure region. The goodness of fit graph shows the same data that we saw on the previous slide. However, this time we're not looking at it on a log axis, but a standard axis. It can be a little bit difficult to see here once we get to regions that are below 0.01 P over P naught. Now that we've looked through all the common reports that are available in the software for nitrogen physisorption, next we'll talk about a few different examples that encompass a variety of different reports that we talked about previously. The first example will be silica alumina, where we will look at BET surface area, the PT plot, as well as BGH adsorption desorption. Next up will be alumina, where we will measure BET surface area using krypton, and after that we'll be looking at glass, where we'll look at BET surface area using nitrogen. First up is our silica alumina. Shown here we have the complete isotherm for the silica alumina, which will allow us to collect a variety of information on the sample, including BET surface area, pore size distribution, as well as T-plot information. We can see that this material displays type 4 isotherm and that there is some hysteresis on the isotherm between 0.6 and 0.9 P over P naught. First, let's look at our BET surface area plot. We can see that there's a good agreement here in the standard mesopore range between 0.05 and 0.3, as we have a very linear trend between all of our adsorption points. Looking at the BET surface area data, we can see that we have a BET surface area of 211 meters squared per gram. We can also see our slope and our y-intercepts, as well as our C-value, our monolayer coverage, our correlation coefficient, and the molecular cross-sectional area of nitrogen. In this case, when we look at the BET surface area data, the first two things that I look at are the C-value and confirm that it is a positive number, and then also the correlation coefficient, and ensure that it starts with at least 0.999. Generally, when these criteria are satisfied, it means that the BET surface area data that you've collected is accurate. Next up, we'll look at the Harkins and Jura T-plot area for this sample. We can see that we have very good agreement in the thickness range between 3.25 and 5 angstroms. We can see our micropore volume is very small at 0.00069 cubic centimeters per gram. Our micropore area is 4.1 meters squared per gram. Our external surface area is 206.9 meters squared per gram. We can also see our slope, y-intercept, correlation coefficient, surface area correction factor, density conversion factor, as well as the thickness range that we applied for the Harkins and Jura thickness equation. The important criteria that we're interested in is looking at our micropore versus our external or mesopore surface area, and we can see here for this sample that the majority of our pores are in the external or mesopore range. The combined surface areas of the micropore area and the external surface area should add up to our BET surface area, which we saw on the previous slide. Lastly, we'll look at some BGH pore size distributions. Shown here are our pore volume distributions for our silica alumina. We can see here from the differential and cumulative plots that the majority of our pores are in the size range between roughly 80 and 200 angstroms. Next up, we'll look at our BJH desorption pore volume distribution. We can see that there's been a shift in the size range of our pores, where our pores are smaller, centered between about 70 and 150 angstroms. So the question is, why did our pore size shift roughly 20 to 30 angstroms when we looked at desorption versus adsorption? The reason for this discrepancy is due to hysteresis. When we look at the adsorption and desorption points, we can see that they don't match up exactly. What this means is that we have a larger internal cavity that is only accessible via smaller pores, and what that means is it takes a little bit larger driving force in terms of pressure to remove the gas from those larger cavities through those small pores than what it would take to put the same gas into the sample. What this means for our pore size distribution is that when we measure the BJH adsorption, our adsorption pore size is a combination of these channels as well as these larger cavities. Essentially, we're seeing an effective pore size distribution that counts these larger cavities when looking at BGH adsorption. When we look at BGH desorption, we're only looking at these smaller channels and not the larger cavities. In general, it's recommended that whenever your sample displays hysteresis, that if you're going to use BGH, you want to do pore size distribution using the desorption branch to account for the hysteresis loop that occurs. In general, BGH is a great technique for determining the pore size distribution of pores between 30 and 1,000 angstroms. In summary, for silica alumina, we saw that we had a BET surface area of 211 meters squared per gram, a total pore volume of 0.73, which was calculated close to saturation when P over P naught is close to 1. We had a BGH adsorption average pore width of 103 angstroms and a BGH desorption average pore width of 86 angstroms. The data that was used to determine this was the BET surface area was calculated in the standard range between 0.05 and 0.3 P over P naught. The pore volume was calculated near saturation, and the BGH Adsorption, desorption were calculated between the range of 0.3 and 1 relative pressure. The next sample we'll look at is alumina measured for BET surface area using krypton. We see a much different isotherm for this sample than the previous sample because we're only interested in the surface area, so we don't need points outside of the range typically used for BET measurements. For krypton, oftentimes you'll collect these points between 0.05 and 0.25, so a little bit narrower range than what you might typically use for nitrogen. Looking at our fit, once again, we see an excellent fit in our BET surface area plot. We observe a BET surface area of 0.25 meters squared per gram, a slope of about 20.8, and a y-intercept of 1.2. Once again, we have a positive C value, very small monolayer coverage amount of only about 0.04 centimeters cubed per gram STP, and a correlation coefficient with at least 3 lines. The molecular cross-sectional area displayed here is for krypton, which is a little bit larger than nitrogen. You might be wondering, when should I use krypton to measure the BET surface area of my material? In general, krypton is better than nitrogen for low specific surface area materials. There's not a hard, fast set point where krypton becomes better than nitrogen in all materials, but starting around 5 meters squared per gram, you may find that your krypton data is better than your nitrogen data. What can also play into this is when you should use krypton over nitrogen is the density of your sample and how much sample you can load into a sample tube. This is important for low density samples where you cannot load very much sample. Also, if you're only able to produce and analyze a small quantity of material that has a very low surface area, you may also find it beneficial to use krypton versus nitrogen. Next up, we'll look at BET surface area of another low surface area material, but this time using nitrogen. This isotherm looks very similar to the krypton isotherm that we looked at previously, and we're only really interested in the standard BET surface area range. Once again, we see excellent fit in our BET surface area plot. Looking at our surface area for this material, we obtain a BET surface area of 7.8 meters squared per gram, and we also see a positive C value and at least 3 nines in our correlation coefficient. Now let's look at some of the pros and cons of krypton versus nitrogen. Krypton tends to be quite a bit more expensive than nitrogen. Krypton measurements, however, only use a very small quantity of gas for each measurement, compared to what you'd use for a nitrogen measurement. Additionally, you'll also use liquid nitrogen to maintain the temperature of the dewar, which is the same as what you'd use for a typical nitrogen physisorption experiment. You may find that krypton is a little bit more accurate when determining the surface area of samples below 5 meters squared per gram, and you can measure down to roughly 0.01 meters squared per gram accurately. Nitrogen, on the other hand, is cheap, as is liquid nitrogen, and you'll conduct the measurement using liquid nitrogen the same as you would for krypton. You can measure down to about 0.1 meters squared per gram using nitrogen. However, you may find that it's a little bit less accurate than krypton below 5 meters squared per gram. And oftentimes you'll need much more sample to collect a nitrogen measurement than krypton. The last sample we'll look at today is a microporous carbon carbosieve S3. In this case, we're mostly concerned with the BET surface area and are only collecting adsorption points up to 0.3. However, we do expect this material to be microporous, so we will try to collect as many points below 0.01 as possible. Looking at our BET surface area plot, we can see a good fit in the very low pressure range. What this means is that we will likely need to use the Roquerol approach to determine our surface area, as opposed to the standard 0.05 to 0.3 P over P naught that we would use for a mesoporous material. For microporous samples, it's recommended to use the Roquerol BET plot to select your adsorption points. In general, what you want to do is select all the adsorption points up to where you reach the maximum in the Roquerol BET plot. This will correspond to a positive C value, and in many cases will result in a correlation coefficient with at least 3 nines. Looking at our BET surface area, we can see that this sample has substantially more surface area than all the other samples we looked at so far. The BET surface area of this sample is roughly 770 meters squared per gram. We can also see a positive C value and a correlation coefficient with at least 3 nines in it. Next up, we'll look at the Horvath Kawazoe pore size distribution for this material. As expected, this material is primarily microporous, with pores right around 5 angstroms in size, where we have the largest distribution of pores. Horvath Kawazoe works great for determining the pore size distribution of materials with pores less than 30 angstroms in size. To summarize what we talked about today, we showed a variety of different reports that are available in our software, primarily focusing on reports for surface area analysis, where BET method is the most commonly used method. We also talked about some of the differences between krypton versus nitrogen measurements, and we talked a little bit about pore volume and area distributions, including the BJH method, which is primarily used for mesoporous materials and very often collected on a variety of our instruments, including TriStar, ASAP 2020, as well as the 3-flex. For materials, we looked at silica alumina, a low surface area alumina, a low surface area glass, as well as a microporous material carbosieve S3. Thank you for watching this video. If you have any questions, visit micromeritics.com.